Welcome to Talkcast, and back to my ongoing breakdown of The Fabric of Reality by David Deutsch. Today we are up to Chapter 11, Time, the first quantum concept. And today is going to be the first episode in what I expect to be a rather lengthy series. Time is a subtle concept, and today is more like an episode 0 even than an episode 1. We will get to some readings, but they will form the smaller part of the episode, which is going to be an introduction to various ways of looking at this concept that we refer to as time, which ancient thinkers have pondered and grappled with, and, well, St. Augustine put it best, where he says, quote, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." End quote. David pretty much begins the chapter with this quote that we'll see, but it's been used and repurposed over and again by physicists to explain the depth of the mystery that is time. Of all the features of reality that physics studies, none compares emotionally to that of time. Maybe you're worried that your home has a lack of space. There's some worry about space. Perhaps that loud lightning bolt now makes you afraid of thunderstorms, so electricity can cause fear. Perhaps the awe and wonder of seeing an image taken by the James Webb Space Telescope inspires you. There is much to connect to in an emotional way to the physical sciences, our new discoveries, and things that we encounter day to day that physics actually looks at, which can have an effect on us psychologically. But absolutely none of them hold a candle to time. Time is nostalgic, poignant. It is the essence of hope and regret, two emotions contemplatives strive to detach from. They want to live in the present moment, they say, neither dwelling on the past nor being concerned about the future. In a sense, to live time-free, perhaps. It is almost as if there are two kinds of time, the time that physics studies and the supposed experience of time that we people apparently have. What time is has always been more mysterious than what space is or what matter and energy are, at least to the typical person, and perhaps even to the professional physicist working in these areas.
But we still have time.
Time? What time do you think we have?
I even heard time referred to recently as a terrifying concept.
You could be terrified by, time is a terrifying concept. And
this was a great little video about mathematics that David Deutsch tweeted out and I watched, and fortuitously, time was mentioned near the end of this particular clip. I recall myself when studying geology, as I've mentioned before, for a few semesters, and a lecture series turned to what is known as deep time or geological time. And when encountering this idea, gradually over the course of, let's say, a semester of studying geological eras and periods, students, one after another, would eventually come to some realization that when we were talking about geological eras, we were speaking about timescales that moved from being barely comprehensible to somehow emotionally stirring. People would gasp and wow at just how long ago and for how long things endured. Geological and cosmological time is tough to get one's head around. One reason is not that geological or cosmological or even evolutionary time is so long, but that human lives are so ridiculously short. It's a travesty. Yes, we are among the longest lived creatures on Earth, but at barely 100 years lifespan if you're lucky, or not so lucky, more healthy, wealthy and wise these days. This 100 years is a puny amount of time to be around. So every moment is precious. And the health and medical industry are among the most profitable businesses on the planet for good reason. People want to add more time and more quality time to their lives. All the talk now is about longevity and even for some, immortality. And as we say here, if no law of physics rules it out, such as for immortality, then what stands in our way but a lack of knowledge, knowing how to live forever? We, almost all of us, want more time, not just in our lives, but in the day. And if we were all optimists, we would all want more time. And not just for ourselves, but for everyone else as well. And here we'll ignore, except for a passing comment, those intellectuals who have argued themselves into a death cult, where it's good somehow that one generation passes on to make room for the next generation. They are, of course, the worst kind of pessimists, not to mention ageists, and, well, anyone who argues that kind of thing, you can sort of guess the rest of their worldview. They're going to be environmentalists who hate the West. They inherit, or rather have rediscovered, ancient wisdom found in the holy books. It's good to die. Something better awaits. It's all a modern death cult, as I say, people who argue against longevity research or even immortality. Well, we're not going to have that here. We want more time and more life and more flourishing of people. We want more people with more time. Time is almost an obsession for many, and for good reason, both inside and outside of professional physics. It goes beyond mere curiosity. We lose people we love dearly and would love to speak to them again. Could we? Can we? Is there a way to time travel? Could we change the past? Or perhaps at least glimpse it again in full fidelity once more by being there? Or as I say, finally gain the holy grail of eternal life? People speak of making the most of their time, not their space, because we sense only the former is limited. There's enough space to go around. We wonder about what we'd do if we could have our time over again. When we're told, your time's up, we're rarely relieved at hearing those words. Unless, of course, it's the end of a stint in prison. We're told it's time to go, and off we go. The very word time features in more English phrases and cliches than just about any other noun. Language itself is moulded around moments. The passage of time seems to change. If we're in a traffic jam or the dentist's waiting room, 5 minutes seems like 15. But on the other hand, a long dinner filled with laughter and friends might seem like it goes by in a flash. It's as if our sense of time is tied to our noting of change in the world. If little is changing, time seems to move slowly. If a lot is going on, all our senses filled with events, time seems to move fast. But then people who report being in accidents where everything happens fast report things slowing down. What's going on there? Time, our experience of it, seems to have something to do with memory and the vividness with which we can recall a memory. And as you get older, everyone has the same experience. The older you get, the faster time seems to go. When you're 7 years old, a year seems to be indescribably long. Once you're past your 40s, Christmases and your own birthdays seem to come around much faster than they ever have before. Subjectively, time seems to dilate, which is to say, it seems to stretch or contract depending on what we're doing and how much time we've already experienced, or our age, in other words. Objectively, time does dilate, of course, but for different reasons. Two observers moving through space at different rates measure the passage of time differently. Two observers in similar places but experiencing differently the effects of gravity will experience time differently as well. And two observers separated by vast distances do not share a common time. Well, in fact, let's be precise. Strictly, none of us share a common time. We each carry our own individual times with us. But for day-to-day, for most intents and purposes, as they are, we never notice that difference. It's only to be found in the 15th decimal place of how many seconds have gone past. But I'll come back to the actual physics of all of this shortly, as far as we know it. Nothing quite stirs the same feelings within us as old photographs of ourselves, those we know which enable us to recall times past. Those photos seem to capture snapshots of universes that once were, but which have passed. Times and places that were so very different to what feels modern and somehow so much more fast-paced now. There in those old photos, there seems to be no change. We will come to see that this idea of the past being like a different universe, literally, is true. It's not just that that's like a different universe, but perhaps they are different universes. That, in fact, is our best understanding of modern physics. Those old photos, the images there, they're still. Nothing changes in them. And even if we have old movie footage where things are moving, it's predictable. So Nothing really changes there either. And yet in our real world, not the recorded world, change does happen. And perhaps only change happens. And aside from that, there is actually no time independent of change. I'm going to explore part of that idea today. That implies that perhaps time doesn't exist after all, and what exists according to our criteria set out in that other book, The Beginning of Infinity, is that a thing exists if and only if it features in our best explanation of something. But as we will explore, perhaps, our best explanation of the universe is that of a block universe where there is no ticking clock, where nothing changes, where there's no time. In which case, what is this word time referring to? Is it just a subjective experience we are all having? Yet physicists measure time, don't they? We all do. Everyone does, all the time. Well, yes, but people also claim to measure the force of gravity, and we know what we've said about that. So today does begin a deep dive into time. How can we understand this thing? What does the classical physics of Newton say about this thing? What does Einstein's relativity say? And finally, what do the most cutting-edge understandings coming out of quantum theory say about time? Along the way, we're going to consider that controversial question I've just raised. Does time even exist? Is it a real thing? Perhaps only change exists, as I said. But for now, let's ignore those subtleties. The physical sciences talk a lot about rates of change, and those rates of change are often with respect to time. Time is supposed to be the constantly ticking, completely independent, smoothly flowing quantity against which other kinds of change are compared. This is the Newtonian view, that time ticks away inexorably, somehow outside of the universe. 1 second per second goes past. It's the same for everyone, everywhere, at all points. It's a continuous quantity as well. You can divide it up infinitely. There's no smallest unit of time. And forget about the Planck time. That's not the smallest unit of time. It just puts a boundary on what we can measure. But classically speaking, there's no limit, not only to time, but to how precise you can get in measuring time. If here today it's March the 3rd, 2024 for me, then so too is it for someone in the next room, unless we're either side of the international date line or something. And yet, we know, as a matter of fact, from relativity, that people do not experience the same time. And so let me explain that. This idea that the time you measure between any two events is not identical to that which another person travelling at a different velocity is going to measure. That's the first physics fact I want to introduce here now, as we're talking about time. This podcast, of course, being an introduction to all these matters that are discussed in physics and philosophy. This one is crucial, I think. And anyone who encounters this amazing fact that I'm about to explain to you about our world should pursue it as far as they're interested, because the depth of this is very great. And this is just the tip of the time iceberg. And that tip is the relativity of simultaneity. I've talked about this on Talkcast before and may even have used the same images at some point. So this is going to be a quick lesson in special relativity. And for audio-only listeners, I apologise, but the only way I can explain this is by using a couple of diagrams. There's no mathematics involved. This is purely a qualitative exercise in understanding sum of relativity. I was disappointed to see recently that a science popularizer and physicist on Twitter was telling everyone how you couldn't possibly really have an understanding of special relativity unless you understood, and he had a long list of different kinds of mathematics, up to and including tensor calculus and linear algebra and all this. And I thought, how deflating for the average person. I don't think that's true. I think that we can understand explanations in physics with the mathematics and without the mathematics. With the mathematics, of course, allows us to make predictions. It allows us to have a deeper understanding. But to rule out the possibility of having any understanding without the mathematics, I think is wrong. And it's the wrong impulse that physicists should have. So I want to show you you can understand something deep, very deep, about the reality of the physical world that we occupy, explained to us first by Albert Einstein. You can understand it without needing to know any deep mathematics. You can just appreciate it from first principles, so to speak. And I don't often talk in terms of first principles, but today it's warranted because special relativity begins with some postulates. They're your principles. Two postulates in particular. They're kind of the brute facts in a sense, but they also form good explanations. And from these brute facts, or from these wider explanations, which form the framework out of which you build special relativity, we can derive a whole apparatus of physics, which has been tested, important to know, over and again against the real world and never violated. Well, certainly general relativity has never been violated. And the same postulates apply there too. The postulates appear in different forms, but I'll just give you and this is my crude explanation from a physics teacher point of view. So professional physicists will have to forgive me for not being formal here. The two postulates are, one, the laws of physics are the same everywhere for everyone. That's pretty uncontroversial. Why should the laws of physics on Mars be different to what they are here for me? Or why should you, if you're traveling in a rocket ship that's traveling near the speed of light, have an experience of the laws of physics that are any different to mine? We both share common laws of physics. That's the first postulate. The laws of physics are the same everywhere and hold the same in all frames of reference, we like to say. No matter where you're going and how fast you're going, the laws of physics hold. The second postulate is the speed of light is constant for all observers. This is a brute fact, and it leads to the correct predictions in the real world. As I say, the first of those postulates is uncontroversial, but the second is something that sometimes trips people up because nothing else is like that. And if you don't see the problem with that, then you have to think through a few thought experiments, I suppose. Like this. If you're traveling in a car that is traveling at half the speed of light, and then you switch on the headlights, how fast do the headlights appear to be going according to someone who is watching the car go past? Well, wouldn't it be 1.5 times the speed of light? A person standing off at the side of the road is going to see the car travelling at half the speed of light. The light coming out of the headlights is travelling at the speed of light. The speed of light plus the velocity of the car together would be 1.5 times the speed of light. But that, according to relativity, is an impossible state of affairs. Why? Because of the second postulate. The speed of light is constant for all observers. So the person on the side of the road can only possibly see, or measure, the light coming from the headlights as travelling at the speed of light. The person in the car, likewise, when they switch on the headlights, notices the light streaking away from them at the speed of light. Everyone agrees that the light coming from the headlights, no matter how fast they're travelling, will be travelling at the speed of light. This seems to violate people's common sense understandings of how relative velocity works. And again, I would look into this if you're interested or if you don't know what I'm talking about. In any case, the postulates are true because we can test the special theory over and over again, and its consequences, which rest on that assumption, are found to hold. On the other hand, if you do go with the common sense notion that the speed of light can change, nonsense follows. And the observations you make in the real world do not match what is predicted by your theory, which would be something like Newton's theory of motion and relative velocity. When I say light, by the way, it's important that we distinguish rays or beams of light from individual photons. It's the photons that travel always and only ever at the speed of light. A photon going through glass is absorbed and re-emitted by the silicon atoms in the glass, and therefore the ray, which is a collection of photons, takes more time to go through the glass than it does through an equal thickness of air. This is not because light slows down in glass, as the common and wrong explanation goes, but rather because the time taken for a photon to be absorbed by the glass and then be re-emitted takes time. But individual photons never deviate from the speed of light. The speed of light, by the way, is 299,792,458 meters per second. And it's exactly that, and defined as that. So it can't actually be measured. The speed of light can't be measured. I'm not going to go into that fully now, but the point is that the meter, the length of a meter, is defined in terms of the speed of light and not the other way around. The speed of light is the fundamental quantity. The meter, or lengths, are derived from the speed of light. For more on that, see Michael Murphy's page here. He is a physicist who studies light, and he's also a physicist who studies the possibility of the changing constants of nature. So if the speed of light did change, his point here in this article is we could never know. Isn't that interesting? Anyway, the speed of light being 299,792,458 metres per second is a rather clumsy number, but it's very, very close to 300 million. So that's easier to say, easier to remember. 300 million metres per second. But physicists who like to condense and truncate things usually write it as 3 times 10 to the power of 8 metres per second. So that's what I'll use. And that is the constant. Again, if you're still not convinced that the speed of light is indeed constant for all observers, look up the history of special relativity. Look into the Michelson-Morley experiment, among other things, and you can persuade yourself of this counterintuitive fact. The Michelson-Morley experiment didn't prove, so to speak, the speed of light is constant, but it showed that there was no luminiferous ether, and it comes to bear on this question. But if you can take the fact on board, if you can just accept it now, that in fact it's required that the speed of light be constant for the special theory of relativity to work, and therefore us to be able to, and all physicists to be able to explain the world as they do, and to run experiments which do not contravene the special theory of relativity, but rather the special theory of relativity's predictions agree with the outcome of experiments. In other words, the special theory of relativity really does explain what's going on in the world. Then you're forced, logically, to accept the speed of light is constant. So let's have a look at this relativity of simultaneity thing and see what bearing it has on this question about the nature of time. So I'm going to attempt to explain the relativity of simultaneity. One of the very first concepts that people who study special relativity encounter. One of the most exciting and counterintuitive of all of the ideas in relativity. It just gets more interesting from here. But once you grapple with this, you can grapple with the rest. The idea classically, prior to Einstein, was that if something happens at the same time, for me, then you would agree that it happens at the same time. But here's an artificial one that I'm going to make up. It's a common thought experiment, as happens in discussions of relativity quite often. This thought experiment is going to involve a train carriage. And the train carriage has doors at the front and doors at the back. And right in the very middle of the train is a light. And the light can be switched on or off by our observer. Our observer looks to be Einstein in some sandals. Einstein has the ability to switch on the light. Who cares about that? Well, the light is there as a switch itself because the doors at either end of the train are light operated. If the light is off, the doors close, but when the light is switched on, the doors will open. But they'll open only after the light is switched on because it takes some time for the particles of light, the photon, to actually strike the front and rear doors. Because the observer, Einstein, and the light itself are in the dead centre of the carriage, it's an equal length, an equal distance to the front and rear of the carriage. So if Einstein turns on the light now, then photons of light will streak away from the incandescent light that we can see there towards the front carriage and the rear carriage, travelling an equal distance, and will strike the front carriage at the same time it strikes the rear carriage. The light will strike both doors simultaneously. Einstein will say the doors open simultaneously because the light will hit them simultaneously because the light travels the same distance to the front and to the rear. He is, after all, standing right in the middle. There's nothing mysterious about this, is there? If you are outside the carriage, surely you would agree. And you would if the carriage was stationary. However, what if the carriage is moving to the right on my diagram here with some velocity? Einstein has said that the doors open simultaneously. According to Newtonian physics, everyone in the universe, no matter what else is going on, should agree with this. And just because the carriage is moving from the left to the right, let's say, shouldn't change that fact. The light will reach the doors at the same time, causing them to open at the same time. How could it be otherwise? Relativity drives a horse and carriage through this idea. It's bizarre, and it gives you, as I like to keep on saying in these episodes, a strange sense of vertigo if it's the first time you've ever heard it. But that picture, that simultaneous events for one person must be simultaneous for another person, that common sense idea, is false. And here's why. Here we have my second panel. Einstein, once again, is inside the carriage, in the centre of the carriage, just as before. The only difference here is that the carriage is going to be moving from the left to the right. Now, Einstein, inside of the carriage, switching on the light, notices nothing different. He might look out the window and notice some things different, but inside the carriage he notices nothing different. The light still has to travel the same distance to the front of the carriage and to the rear of the carriage, opening both doors simultaneously as soon as he switches on the light. But outside we have another observer. Let's call her Marie, perhaps Marie Curie. She's outside and she's watching Einstein switch on the light. What does she see? Well, she sees Einstein switch on the light, and she sees Einstein standing in the centre of the carriage. But when that light is switched on, what she will notice is that the light will travel towards the rear of the carriage, which is approaching the light beam. That's indicated by the red arrow. The entire door at the rear moves towards the photons that are heading towards it, and it will open first. It will open first because the photons have a shorter distance to travel. On the other hand, the photons that are emitted from the light and travel towards the front of the carriage, towards the front door, in order to open that door, by the time they get to the position where the door was, the door has moved on because the carriage is moving. It's moving through space. The speed of light is constant. It hasn't increased. It's still 3 times 10 to the power of 8 meters per second. So it has a further distance to go, indicated by the green dotted arrow there. Although the rear door is already open, the front door is yet to be struck by photons of light. Marie, on the outside of the carriage, says the doors do not open simultaneously. The rear door opens first. The front door opens second. This is the relativity of simultaneity. What is simultaneous for one person, one observer, Einstein inside the carriage, is not necessarily simultaneous for someone outside the carriage. In particular, if the carriage is in motion and the observer outside is at rest with respect to the carriage. From outside the train carriage, an observer sees the light travel to the front and rear doors, but the rear door moves towards the light, so opens first, while the light must travel further to catch up to the front door, which is moving away from it, so it opens later. The forward and rear rays travel different distances, but inside the carriage, they travel equal distances. This is an amazing fact. And moreover, there's no lower bound on v, the velocity at which the carriage is moving. In other words, any motion whatsoever will strictly cause events for one observer to occur at a different time to those of another observer. But day to day, no one ever notices this, of course, because v is too slow. V has to be close to the speed of light before it's noticeable. But noticeable is not actual. The actual situation is that we all have our own unique nows. There is no objective universal now throughout the cosmos. For Einstein, inside the carriage, now meant this and that door open simultaneously. But for anyone else, which is anyone outside the carriage, outside his, or rather anyone not co-moving, as we say, with his carriage, now is different. So if you get that, well done. You've understood the basics of special relativity. Take a deep dive now into time dilation as a simple formula, or length contraction, and then move on to E equals mc squared. It's not hard to get there. It really isn't. People teach this stuff over a course of a few days, and they become quite proficient in understanding the theory. You don't need hard mathematics. If you can solve a square root and perhaps do a little bit of trigonometry, you're done. You don't need higher order mathematics to glimpse the basic underlying ideas here. So I've just explained how now is unique for everyone. Yet it also feels special, but it's not any more special now than that here is special. You're always here now. Those words are indexicals, here and now. An indexical is a strange kind of word whose meaning depends on context. What does now mean, after all? Well, it depends on who's saying it. And that is literally true. The version of yourself from yesterday is experiencing now. You are experiencing now. You are not your version, strictly speaking, from yesterday, although you share almost all memories and dispositions with them. This, by the way, is why, morally speaking, you're responsible for what that version of you yesterday did, and you're also entitled to what they were, but now is different for different people.
What the hell am I looking at? When does this happen in the movie?
Now. You're looking at now, sir. Everything that happens now is happening now.
What happened to then?
We passed then.
When?
Just now. We're at now.
Go back to then.
When?
Now.
Now?
Now.
I can't.
Why?
We missed it.
When?
Just now.
So, the relativity of simultaneity illustrates something about now, and how now is not unique. It's not a universal. It's different for you and me and for everyone else. That's among our best understandings of time. That which comes from relativity, and it ties time also directly to space and motion. Where you are in space and how you are moving affects time. It also affects space, by the way, but that's another matter. I'm not sure if anyone's screaming at the screen yet or at their smartphones. Brett, this chapter is titled Time, the First Quantum Concept. You haven't mentioned anything about quantum theory. Yes, that's a bit awkward, isn't it? I've been talking relativity and time and said nothing about the quantum. That's tricky. But the fundamental point that David will come to is that different times are just special cases of different universes. And that arises out of the work of a couple of other physicists, Don Page and William Wouters, who have devised what has come to be known as the Page-Wouters construction. They were building on the work of Bryce DeWitt, and all of those guys happen to be contemporaries and colleagues of David Deutsch. What is termed today the Page-Wouters construction or Page-Wouters formalism or Page-Wouters mechanism, various ways of formulating that, is a window on time via quantum theory. And of course, I'm no expert on this or much else at all, but I do know someone who is, Sam Kuipers, the physicist, Dr. Sam Kuipers now. And I'll be speaking to him about this in an upcoming episode. But for now, let me say, in reading the work of Sam, who as I say is building on Page-Wouters, it seems time is emergent rather than being fundamental. This we actually already know from relativity after all. Space-time is the fundamental entity there, not space and not time. Space and time are emergent features of this deeper thing that really exists according to relativity, space-time. Space-time is fundamental in that explanation of reality. But a quantum theory of gravity, in other words, the successor theory to both quantum theory and general relativity, will presumably explain time, or space-time, in a deeper sense still, perhaps in terms of Q numbers, quantum numbers. Again, it's something I'll leave for Sam to put a finer point on. In any case, time is tied to change, as I said earlier, and change in the universe may be the deeper concept. After all, if nothing changed in the universe, there would be no ticking. No other thing called time would keep track of the passage of time because there is no passage of time. The world consists of matter and energy, and they are explained by quantum theory, and we can speak about the physical characteristics of matter and energy in terms of quantum mechanics. If all quantum mechanical processes everywhere stopped, there would be no real time. Of course, that very thought experiment violates the laws of physics. We can't just stop things. And when would we stop them if we could? That too makes no sense for reasons I said earlier. There is no simultaneous when. There is no simultaneous way of stopping things. If I am God and say right here and now to stop, well, hold on, I've just said now. So wherever God, unless God permeates the universe, but in which case there's still no singular now at which we would stop everything simultaneously. Physical processes here and physical processes a billion light years away, there's not a simultaneous now that they share. There is no universal when and no universal time when anyone, including God, says stop. This is all fascinating stuff, and we're yet to even mention something like thermodynamics. We're often told that the arrow of time is governed by the second law. The second law, as I've talked about often before, tells us that the entropy or disorder in the universe is increasing. And this is as time goes on. And also, as time goes on, we uncover knowledge and make progress. Now, these things too are fundamental in terms of invoking the existence of entities at a certain level of emergence in order for us to understand what is happening and what is happening to the universe as it evolves. Is it the case, however, that time really does have an arrow, or is it rather that our individual perspective on time or on events or on change is such that we perceive increasing entropy, and in a sense it's opposite happening in lockstep, increasing knowledge, here on Earth at least? The increasing entropy bit is an unavoidable side effect of all physical processes, including the ones we choose to do, as well as the ones that just occur naturally without any intervention by people. But increasing explanatory knowledge is no side effect, nor is it unavoidable. We can choose not to increase our knowledge, which would be the wrong move, and increasing knowledge is an increase of order. But to achieve this, we export ever more entropy to the rest of the universe. But in our little corner, where life, and importantly intelligent life, has dominion, we can keep exporting that entropy to a universe that keeps getting ever larger, and in the meantime make our corner of the cosmos better. But here I have invoked the concept of choice and linked it to knowledge. We will get there too in this chapter in a subsequent episode. This is really just a teaser for what's to come. Now, I'm going to get to some readings from the Fabric of Reality today, but before I do that, I want to bring in another master of science writing, and one who has been interested in time for basically his entire career. And I could have chosen amongst almost any of his books, but I'll pick his most famous and most lauded, The Mind of God. Of course, I'm talking about Paul Davies. So I want to just read the very beginning of chapter 2 of this book. Just a few sentences. The chapter is titled, Can the Universe Create Itself? You can possibly see the yellowed and fraying pages of this old copy. Davies writes, quote, "We usually think of causes as preceding their effects. It is therefore natural to try and explain the universe by appealing to the situation at earlier cosmic epochs. But even if we could explain the present state of the universe in terms of its state a billion years ago, would we really have achieved anything except moving the mystery back a billion years? For we would surely want to explain the state a billion years ago in terms of some still earlier state, and so on. Would this chain of cause and effect ever end? The feeling that something must have started it all off is deeply ingrained in Western culture, and there is a widespread assumption that this something cannot lie within the scope of scientific inquiry. It must be, in some sense, supernatural. Scientists, so the argument goes, might be very clever at explaining this and that. They might even be able to explain everything within the physical universe, but at some stage in the chain of explanation, they will reach an impasse, a point beyond which science cannot penetrate. This point is the creation of the universe as a whole, the ultimate origin of the physical world." End quote. And it's a reasonable impulse that people would have. However, one way of getting around this, and it's not trying to be too slippery by half, is to recognize that physical reality consists of matter and energy, yes, but also the space-time in which that matter and energy manifests itself. And so if you want to explain physical reality, you've got to explain the origins of space-time. You've got to explain the origins of time. So it becomes a bit difficult to talk about a time before time existed. And so this leads to the usual ways in which physics is done breaking down when it comes to trying to explain time. Because as Davies has said there, normally we talk in terms of causes and their effects, using dynamical laws. All of what Davy says there, quite rightly, illustrates a hole at the heart of the usual way of formulating those very questions of cause and effects, especially when it comes to something like the origin of the entire universe. The earlier times dictating the latter, when under time-symmetric laws like those of quantum theory or relativity, we may as well say that the later events dictate the former, because the laws are time-symmetric. This problem seems to point to a deeper theory, a deeper mode of explanation, to get beyond those time-symmetric laws of physics, the dynamical laws. Hence, let's raise one other physicist author, Chiara Mileto, in The Science of Can and Can't, and what she says in, coincidentally, her own chapter 2. That's titled Beyond Laws of Motion. And Chiara writes, quote, "But in the case of the universe, this constitutes a problem. What is the clock to time its evolution? The universe contains everything by definition. There cannot be anything external to it, let alone a clock. These are two faces of the problem of time, which affects all dynamical laws when regarded as ultimate explanations. Incidentally, this problem also affects laws as formulated in general relativity, where instead of a single external label, time, you have the set of labels specifying a point in space-time. The same problem presents itself as far as space-time itself, which is left unexplained. Here I do not wish to expand on the solutions to this problem. My point is just this. Whatever the solution to the problem may be, it cannot be given in terms of initial conditions and dynamical laws. Otherwise, it falls into an infinite regress. It must be given in terms of some other kind of explanation. Some proposed explanations already exist. If you are interested in reading about them, beautiful accounts are in Julian Barber's magisterial treatise, The End of Time, and in Michael Lockwood's intriguing book, The Labyrinth of Time, end quote. And I couldn't agree more. I've read both of those, but it was some years ago. In fact, it was in the interglacial period between the fabric of reality and the beginning of infinity, where I was hungry to read anything that David Deutsch might have recommended. And I think that at least one, in the fabric of reality, he recommends one of those books. I think it's Michael Lockwood's book anyway. But what Chiara has said there is quite right. We may need to get beyond dynamical laws and initial conditions. We could get beneath time if we consider not what happens when and what leads to what, but rather what's possible and impossible, perhaps. And if there is no external clock, and there isn't, and all clocks are internal and physical, not some sort of abstract ideal thing, which implies an external ticking, then the keeping of time emerges from quantum laws of physics. But for more on that, I'm going to need Sam Kuipers, as I say. But enough of the lengthy introduction. It's more than an introduction. It's most of the episode. Let's go to the fabric of reality now. Chapter 11, Time, the First Quantum Concept. And David begins with a quote by Shakespeare. Quote, "Like as the waves make towards the pebbled shore, so do our minutes hasten to their end, each changing place with that which goes before, in sequent toil all forwards do contend." End quote. William Shakespeare, Sonnet 60. David goes on to say, quote, "Even though it is one of the most familiar attributes of the physical world, time has a reputation for being deeply mysterious. Mystery is part of the very concept of time that we grow up with." And then he quotes the St. Augustine quote, where St. Augustine says, he knows what time is until someone asks him what it is. And then David goes on to say, quote, "Few people think that distance is mysterious, but everyone knows that time is. And all the mysteries of time stem from its basic common sense attribute, namely, that the present moment, which we call now, is not fixed, but moves continuously in the future direction. This motion is called the flow of time. We shall see there is no such thing as the flow of time, yet the idea of it is pure common sense. We take it so much for granted that it is assumed in the very structure of our language." And then, end quote. And from here, David goes over the ways in which time might be seen in common sense to be framed by language in such a way as the present moment is in motion towards the future, or maybe the present moment is stationary and the future is moving towards us. In any case, something's moving here through time or in time. it gets all rather confusing. Our intuitions sometimes contradict themselves on this point. So I'm skipping over that couple of pages and I'm picking it up where David says, quote, "To put it bluntly, the reason why the common sense theory of time is inherently mysterious is that it is inherently nonsensical. It is not just that it is factually inaccurate. We shall see that, even in its own terms, it does not make sense." And here we have a diagram, figure 11.1, present moment at a particular point, which we call now, behind which is the past and ahead of which is the future. David goes on to say, when he's just said that common sense does not make sense, he says, quote, "This is perhaps surprising. We have become used to modifying our common sense to conform to scientific discoveries. Common sense frequently turns out to be false, even badly false, but it is unusual for common sense to be nonsense in a matter of everyday experience. Yet that is what has happened here." End quote. And then David goes on to explain that if we try to represent the present moment as part of a diagram, we get caught up in all sorts of contradictions. We want to point to an instant and say this is the present moment, but we simultaneously want to say the present moment is moving. Well, which is it? And at what rate is the present moment changing its position, so to speak? Here's another picture that David has, 11.2. And he says on this, quote, "Consider figure 11.2. It illustrates the motion of two entities. One of them is a rotating arrow shown as a sequence of snapshots. The other is the moving present moment sweeping through the picture from left to right. But the motion of the present moment is not shown in the picture as a sequence of snapshots. Instead, one particular moment is singled out by the arrow, highlighted in the darker lines, and uniquely labelled now. Thus, even though now is said by the caption to be moving across the picture, only one snapshot of it at a particular moment is shown. Why? After all, the whole point of this picture is to show what happens over an extended period, not just at one moment. If we had wanted the picture to show only one moment, we need not have bothered to show more than one snapshot of the rotating arrow either. The picture is supposed to illustrate the common sense theory that any moving or changing object is a sequence of snapshots, one for each moment. So if the triangle is moving, why do we not show a sequence of snapshots of it too? The single snapshot shown must be only one of many that would exist if this were a true description of how time works. In fact, the picture is positively misleading as it stands. It shows the triangle not moving, but rather coming into existence at a particular moment and then immediately ceasing to exist. If that was so, it would make now a fixed moment, end quote. So let's just reflect on that. If we want a diagram to picture what time is like, and we know that there is a future and we know that there is a past, but there's also this moment in time called now that we experience, that present moment is somehow moving. But if you want to illustrate that present moment as being somehow in this flow of time, it is part of all of these different snapshots. After all, it's moving through them. So it was there in the past and it will be there in the future. So why isn't it pictured? How is the present moment singled out? This is a deep mystery. The fact is, we have a perspective. There's a here for us, but there's also a there. And we can turn there into here by walking over there, such that there will become here. That's not that mysterious. We carry it with us. Now with time, the same kind of thing is going on. It's an analogous situation. We have a perspective on time, and we can see part of it. We experience or are conscious of part of it. Subjectively, we have the experience now, but now is not special except for the fact that we are experiencing. In the same way that here is not special. Me, I'm sitting in Sydney. There's nothing special about the fact that I'm here experiencing Sydney. I know that London and Paris and New York also exist, as much as Sydney exists. And there are people conscious there now. And I would be conscious there now too if I hopped on an aeroplane and went there. In the same way, the past is just as real as now, which is just as real as the future. And there are conscious entities there experiencing those as now. I know it's hard to accept. Jaron Lanier makes this point that people who don't accept the mystery of consciousness get tied up with the mystery of the present moment now. Because if you don't think that there's a mystery there at the heart of consciousness, then you have to explain why the present moment is singled out as different to all other times. On the other hand, if you say that time is not particularly mysterious, this way of trying to understand time, then you have to explain why it is that you're conscious of this time and not all the other times. Well, the fact is, you are located at a particular point in space and time, but you can move through that space-time. And you are moving through the time, and you can move through the space. It's just that you can't choose the rate at which you can move through time. As you're sitting there, you are carried inexorably in some way. But that, of course, contains a misconception that implies a flow of time. You're being carried. You're experiencing change is a better way of putting it. Skipping a little, and David says about that diagram, at best one could say that figure 11.2 is a hybrid picture, which perversely illustrates motion in two different ways. In regard to the moving arrow, it illustrates the common sense theory of time, but it merely states that the present moment is moving, while illustrating it as not moving. How should we alter the picture so that it will illustrate the common sense theory of time in regard to the motion of the present moment as well as the motion of the arrow? By including more snapshots of the triangle, one for each moment, each indicating where now is at that moment? And where is that? Obviously, at each moment now is that moment. Skipping a little, and David has another image, figure 11.3 here, and on this he says, quote, "This amended picture illustrates motion satisfactorily, but we are now left with a severely pared down concept of time. The common sense idea that a moving object is a sequence of instantaneous versions of itself remains, but the other common sense idea of the flow of time has gone. In this picture, there is no continuously moving point, the present moment, sweeping through the fixed moments one by one. There is no process by which any fixed moment starts out in the future, becomes the present, and is then relegated to the past. The multiple instances of the symbols, the triangle, and now, no longer distinguish one moment from others, and are therefore superfluous. The picture would illustrate the motion of the rotating arrow just as well if they were removed. So there is no single present moment, except subjectively." End quote. That last sentence bears repeating. Contemplatives everywhere can cogitate on this. Quote, "So there is no single present moment except subjectively." David goes on to say, "From the point of view of an observer, at a particular moment, that moment is indeed singled out, and may uniquely be called now by that observer, just as any position in space is singled out as here from the point of view of an observer at that position. But objectively, no moment is privileged as being more now than the others, just as no position privileged as being more here than the others. The subjective here may move through space as the observer moves. Does the subjective now likewise move through time? Are figures 11.1 and 11.2 correct after all in that they illustrate time from the point of view of an observer at a particular moment? Certainly not. Even subjectively, now does not move through time. It is often said that the present seems to be moving forwards in time because the present is defined only relative to our consciousness, and our consciousness is sweeping forwards through the moments, but our consciousness does not and could not do that. When we say that our consciousness seems to pass from one moment to the next, we are merely paraphrasing the common sense theory of the flow of time. But it makes no more sense to think of a single moment of which we are conscious moving from one moment to another than it does to think of a single present moment or anything else doing so. Nothing can move from one moment to another. To exist at all at a particular moment means to exist there forever. Our consciousness exists at all our waking moments. Skipping a little, David goes on to say, we do not experience time flowing or passing. What we experience are differences between our present perceptions and our present memories of the past perceptions. We do not experience time flowing or passing. What we experience are differences between our present perceptions and our present memories of past perceptions. We interpret those differences correctly as evidence that the universe changes with time. We also interpret them incorrectly as evidence that our consciousness or the present or something moves through time." End quote. Brilliant. This should accord with what contemplatives who sit in the quietness of their own mind sometimes say. You hear them talk in similar terms. So people can converge on the truth and come to it via different ways. And this experience of now is subjective. And so what contemplatives are doing, people who meditate, is a purely subjective exercise, even if we can all converge on what's actually happening during those experiences. But the fact is, you don't experience a flow of time or time passing. Rather, you're noticing differences. You're noticing change. Now is different to then. That's all. There's no time that's passing. It's a loose way of speaking. You're not experiencing that. I'm skipping a little more, and David goes on to say, quote, "The idea of the flow of time really presupposes the existence of a second sort of time outside the common sense sequence of moments of time. If now really moved from one of those moments to another, it would have to be respect to this exterior time. But taking that seriously leads to an infinite regress, because we should then have to imagine the exterior time itself as a succession of moments, with its own present moment that was moving with respect to a still more exterior time, and so on. At each stage, the flow of time would not make sense, unless we attributed to it the flow of an exterior time ad infinitum. At each stage, we would have a concept that made no sense, and the whole infinite hierarchy would make no sense either." End quote. As soon as you begin to use this language of flow of time, flow implies a rate. And so if the time is flowing, it's flowing at a particular rate. But how fast? Well, in order to have a measure of that, you would need an external clock, a time external to time, keeping track of the rate of time flowing in this universe. But then if you have that external time, it's moving at a certain rate as well. And so that would need to be measured with respect to an even more external time. And so it goes. And this is why we have, as David says, an infinite regress. That's no explanation. That's no argument. What we experience as time is the rate of change of things. Things are changing. We experience change, we recall change, and we call all of this the flow of time. But nothing is actually flowing. We're not moving through time. We're conscious of a state of affairs as they are. And in the future, we'll be conscious of a different state of affairs, and we'll compare our memory of what was to what is, notice the change, and notice that we are conscious in that moment because we are conscious in previous moments and can remember and notice the change. This is going to take some time to unpack, as you can see. We're barely into the chapter, and I'm going to continue with the chapter. And as I say, promising people, be my only third guest ever will be Sam Kuipers at some point coming up to discuss with me the subtleties of this, because much of this perspective here comes out of the Page-Wouters construction, as I say. And so hopefully by bringing to bear an actual expert on time, I like to call him the Time Lord, Sam Kuipers, we will come to understand in more detail and more depth the best explanation that we have at the moment of what time is, what its relationship to space-time is, and how we can have an understanding of this space-time in terms of quantum theory as well. But until next time, bye-bye.